Hello everyone, my name is Soumya and you're welcome to the fifth interaction session for the course on NPTEL course on control systems. Uh, I am a PhD student at IIT Gandhinagar. So I'll be taking you through the topics that were covered in this week. And the topics that were covered were mostly related to Routh-Hurwitz stability criteria and some questions on performance specifications. Essentially, what you did last time related to peak overshoot and settling time, etc. So all of those stuffs are also there with more clarity, which will give you more clarity. And yes, we'll see the Routh-Hurwitz stability criteria. So last time we had a question in which we wanted to find out for what values of k the system is stable, and it was little bit time taking task to put the conditions like poles lie in the left half of the S-plane. The calculation was also complicated. But this time we have a simpler way, which is Routh-Hurwitz stability criteria, and we'll proceed with it. So, before diving directly into the questions, so we'll just have a look at what is given in the lecture. Just a second. Yeah. So it was made clear that if the polynomial is of this kind, so if it has some coefficients for all powers of s, then what essentially is a Hurwitz polynomial? So a polynomial is said to be Hurwitz if all its roots have negative real parts. So if the poles or the for characteristic equation, if the roots lie in the left half of the S plane, then we are going to say that the polynomial is Hurwitz. So this Hurwitz polynomial would help us know if the system is stable or not. So as we proceed further, we'll see that let's say we have a first order system, and in this first order system, uh, this so what are the conditions that this polynomial would be called a Hurwitz polynomial? So it you can see when we try to find out what would be s for ds is equal to 0, we get that s is equal to minus a1 upon a0. So a1 upon a0 would lie minus a1 upon a0 would lie in the left half of the s plane. It is only possible if a1 and a0 both have the same sign. Both of them either should be positive or both of them either should be negative. So this was essential to have the pole for a first order system to have poles in the left half of the S plane. Similarly, if we take the example of second system, a naught square plus a1 s plus a2. So when would this be Hurwitz? So for this to be Hurwitz, we can see that the pole has, so it's like minus b by 2 and plus whatever you have, so b square minus 4ac a term, plus minus. So whatever this is, this factor would decide if the pole is in the left half of the S plane or not. So if it is in the left half of the S plane, A1 has to be positive. So what we can see essentially is that the pole lie is in the left half of the S plane when A0, A1 and A2 are non-zero and are of the same size. So non-zero is also an important condition here and are of the same sign. So for both of these equations, I mean for n is equal to 1 and n is equal to 2. We can see very well that the poles lie in the left half of the S plane and we get a necessary and sufficient condition just with the help of checking that it is Hurwitz or not Hurwitz. But what if we go for third order system? It becomes too complicated, right? You don't have a general method to find the poles, and it would be very difficult. So for any system which is of third order and above, we use Routh-Hurwitz stability criteria. So, an example that was discussed in the lecture was of this kind that let's say we have a third order, D1 is some third order cubic polynomial, and all the roots lie in the left half of the S plane. But we have another cubic polynomial, and one root is in LHP and two roots in RHP. So you can check this on yourself. So putting conditions such as A1, A0, A1, A2, A3 all should be non-zero, and all of them should have the same sign, just gives us the sufficient condition, and it is not the necessary condition. Sorry, it gives us the necessary condition and it is not the sufficient condition. So we'll see more of such sorts of examples later. But before that, we'll start doing the questions. So the first question is, if all the roots of a polynomial lie in the left half of the complex plane, then that polynomial is called. So definitely we have studied that it is called Hurwitz polynomial. You should have all the poles in the left half of the complex plane. So the second question is similar. So this is a polynomial which is given to you, where k is a real valued parameter, has all its pole in the left half of the S plane. So as we said that the coefficients of all these terms should be of the same sign and should be non-zero. So definitely for s square, s to the power 1 and s to the power 0. For all of them we have non-zero coefficients, that is true. But you see for s square we have the coefficient to be 1, that is a positive number. So for the other powers of s also we need the coefficients to be positive. So k minus 1 should be greater than 0 and k minus 2 should also be greater than 0. When you take both these conditions, you see k is greater than 1 and k is greater than 2. So this is the fact that dominates here, and we want to have k greater than 2 for this. Okay. So we'll have another question here, and that is basically a cubic polynomial. So before proceeding with this, we should see what was given in the lecture. So yeah, as I said, that for polynomials of order 3 and above, a necessary condition for them to a necessary condition is that the polynomial should be Hurwitz polynomial. So necessary condition for them to be Hurwitz is that all the coefficients must be non-zero and of the same sign, that we have seen for the other two systems also. For sufficiency, we construct a Routh array, and that Routh array is constructed like whatever higher power you have, what highest power you have, whatever is the order of the system, you go on decreasing it one by one, and then you have to put the values accordingly. So if this is the case, then like uh, b1 is a1 a2 minus a0 a3. So we arrange polynomials in such a way that a0 comes first, then a1 comes secondary in the same column, a2 is next to a0, and in that way. So it will give you more clarity in terms of the example that you're going to do, and you need not memorize this formula. It would be a matrix kind of multiplication only, but it would not really be a matrix multiplication because the order changes in which like how you take the product, it is of different order here. So we'll see that. So this is for C1 and this is for C2. So what is the crux of this for something for order more than 3? So the number of sign changes in the first column of the Routh array should be 0. If you have any sign change, and whatever number of sign changes you have will basically determine how many poles you have in the right half of the S plane. If there are no sign changes, then you can be assured that all the poles lie in the left half of the S plane. If like there are some sign changes, then you count the number of changes in sign, and those many poles would lie in the right half of the S plane. Okay. So that is what was told. The number of sign changes in the first column of the Routh array is equal to the number of roots of DS in the RHP. All right. So construction of Routh array is a sufficient condition, and we need to check that for ensuring the stability of a system. So yeah, so all of them can be summed in just 2 points, that all coefficients of DS, whatever the polynomial you are supposed to work on, all the coefficients of DS are non-zero and are of the same sign. And secondly, you have to see that the first column of the Routh's array constructed using the coefficients has all entries being non-zero and of the same sign. all have to be of the same sign. There are cases when you get the first entry to be 0, or let's say sometimes entire row to be 0. So that is taken as a separate case. But in general, if you do not have any term to be 0, then you just have to see that the column should have no sign change for the system to be stable, or for the poles to lie in the left of the S-plane. So we'll start with the next question. So we are going to construct a Routh array here, okay? So the way we do this is, uh, let's say, so your polynomial is s cube plus 8s square plus 22s plus 20. So what we are going to do, we'll write it in the order. So it would be s to the power 3, s, s to the power 2, s to the power 1, s to the power 0. Okay, I'll write it again with some gaps because some calculations have to be done. So we write it in this way. Now what we are going to do is, just a second. Now what we are going to do is, we are going to write the coefficients. So here in this case, it would be 1. You'll write 1 here. For s square, you'll go to the next line. The 8 coefficient would be here. Then you would write 22 again here. Then 20 would be here. Okay. Once you are done with this, what you're supposed to do you're supposed to calculate what would come for S1. So it would be like 8 into 22 minus 20 into 1 upon 8. So how it goes? You multiply both of these terms, then you subtract the multiplication of these terms. So in matrix, you might have seen you would do 1 into 20 minus 8 into 22 in normal matrix multiplication kind of thing. Or when you, not multiplication, it would be finding the determinant. So you do it like first row, first element to the last element of the next row for a 2 cross 2 matrix. But here you are not supposed to do that. Rather, you have to take it in opposite way. So 8 into 22 minus 20 into 1 divided by the last element that you had for the previous power of s. Okay. So when you try to calculate this, you would get it to be equal to 19.5. And if you get 19.5, then you would repeat the same thing. So it would be 19.5 into 20 minus 8 into 0. Why 8 into 0? So I'll replace it with 19.5 now. So here you don't have anything, it means you have 0 here. So 8 into 0 upon 19.5. This would again give you just 20. Okay. So what do you observe here? Is there any change in sign in the first row? So I'll remove this again and write 20 here. So just check this thing. What you can see is that all of them have positive sign, means there is no sign change. No sign change means how many roots you were supposed to have for this equation? This is a third order polynomial. So how many roots you would have? Since it is third order, you're expected to have 3 roots. And since there is no sign change, so you will have all the roots in the left half of the S-plane. So you can rest assured that there are 3 roots in the LHP. Okay. So this was the case that we have seen. Now we'll move to the next question. And it is also of similar nature. But what we're going to do here is the same thing, and let's see what we get after the calculations. So I would urge every one of you to start solving this on your own, because I would not be constructing this Routh array. I expect the answer from the audience. So you would have 1 here, 5 here, 2 here, 12 here. I need the answer for this element and this element. Has someone solved? I hope I am audible. Yes, it would be minus 2 by 5. Yes. So the answers that we would get here is basically minus 0.4 and 12. Okay, so we can observe here very clearly that there are two sign changes. So here 1 to 5 there was no change. When you move from 5 to minus 0.4 there is a change. And when you move from minus 0.4 to 12 there is another change. Okay, so we can observe that there are two changes in signs. What does that imply? This means that so it is a third order polynomial, so there are three roots. Now there are two sign changes. So one root is in LHP, two roots are in RHP. So this is the conclusion that can be made from this polynomial. Okay. So there was another case that was discussed with you. Just a second. There was another case that was discussed with you, and it had the first element of any row of the Routh's array is 0, with the other remaining elements being non-zero. So this is one of the case. So in case you are trying to solve the Routh array and somewhere you find that you get a 0 in the column, then what you're supposed to do? So one of the ways in which we deal with it is we replace the 0 with a very small real number, positive real number, epsilon. And then we continue the process and then we try to observe if there are changes in the sign. But appearance of 0 in the characters in the equation is itself something to be considered, because in general you do not get 0. So in case you are getting 0, that means that there is a complex root definitely. And if just a column is 0, that means that there is a pair of root on the imaginary axis. If the entire row is 0, it is some other condition of radially opposite roots. But if just one of the elements is 0, the first element is 0 in any row, then you would know that there is a pair of root on the imaginary axis. Okay, so that is what is told here. So if there is a sign change from the entry above epsilon in the first column to the entry below epsilon, then there are roots in the right half of the S-plane. Okay. If there is a sign change, then only. If there is no sign change from above epsilon to below epsilon, then there is a pair of root on the j omega axis. Okay. So let's proceed with the following question. So again, we try to find out what is the Routh for this, and you'll see. So it is fourth order. That means we are going to have four roots. Now let's see where are the roots located. So how you write this? 1, 3, 6, 12, 8, right? You can find out s square and it would be uh, 1 in, sorry, it would be 3 into 6 minus 12 into 1 upon 3. The second element would be uh, 12 into 8 minus 6 into 0 upon 12. Okay. So when you try to find out the
Madam, it's
answer,
like 3 into 8 by 3.
sorry, yeah, correct. 3 into 8 minus 1 into 0 upon 3. Thank you. So when you write this, yeah, this is correct. So when you write this, what you get here is this would be this whole term and this whole term. This would be 2, so 18 minus 12 by 3. So this would just be 2 and this would be 8. Okay. So when you proceed for the next step, what would happen? So it would be 3 in, so 2 into 12 minus 3 into 8 upon 2, and this would be 0. When this term is 0, what you would do is replace this 0 with some epsilon. Okay. After replacing it with epsilon, again try to find out the answer. 8 epsilon minus 2 into 0 upon epsilon. So you'll get it to be 8. So when you try to track the sign changes, you will see that there is no sign change from here to here, and there is no sign change from here to here. Okay. So since there are no sign changes anywhere in the RH table, the roots definitely uh, do not lie in the right half of the S plane. This is clear now that no roots in RHP. Okay. But we still need to check where are the roots lying. So if this one element was 0, the first element was 0 for any row, that means that there are imaginary roots on the imaginary axis. And how we can find them? We can find them. So anything that you write corresponding to this would give you the auxiliary equation. So it is basically 2s square plus 8. Why 2s square? Because 2 is here. It is corresponding to s square. And definitely in the second term, wherever you might have seen the order, the power of s is decreased by 2 is equal to 0. So from here you can see s is equal to plus minus 2j. So these are two roots. So you would have two roots. Yes, you would have two roots in LHP, two roots on imaginary axis. So you have two roots on imaginary axis. Okay. So, yes. So in the last class, we saw that we were trying to stabilize the system with some proportional controller or derivative controller. That way we have another question here. And you can check if we can stabilize this using proportional controller, or we need a derivative controller, or just integral controller would serve the purpose, or proportional integral controller would serve the purpose, or we need proportional derivative controller. So we can check all the options here, but in general cases derivative is also needed. And yeah, because this would give you the answer. So I would start with solving this, and similarly, you can check all the other options also. Okay, so we'll just proceed with the this condition first, PD controller. So what we would do is y double dot t plus yt is equal to ut. Now, when we take the Laplace transform, it would be s square ys plus 4ys is equal to us. Okay. Then, since I want to check proportional derivative controller, so your CS would be Kp plus Kds, right? Once you have this, so what would be your GS? We saw earlier that this is RS. Then the reference input. Then what you do? You get an error. I'll show from where the error comes. When the error comes, it is passed through a controller. From controller, you get the control input, which is passed to the plant, and from plant you get the output, and that output is multiplied by some feedback gain, and it is given as an error. So here in this case, this whole thing, so sorry, this is not GS, this is PS. So here in our case, this whole thing, this GS. So what is your GS? PS into CS. Okay. Once you get this, what we can write? Kp plus Kds upon. From here you had ys upon us to be 1 upon s square plus 4. So here you would get s square plus 4. So what is your closed loop transfer function? How do you write the closed loop transfer function? What is the formula that was derived in terms of GS, HS? So if you remember from your lectures, it is GS upon 1 plus GS into HS. And since the question very well says that it is a unity negative feedback, so HS is definitely going to be 1 here. What we are going to do is, we want to find out the stability condition, and stability has to everything to be done with this part of the polynomial only. So what we are doing here is, for stability, we want to find out 1 plus GSHS is equal to 0, so that we can find out what is the characteristic equation. So this is the characteristic equation. Then we would proceed with finding the roots. One thing we can do is, we just want to check if the stability is satisfied or not. So Routh-Hurwitz criteria is a better way of checking the stability of a system. So once you have the polynomial with you, you can apply the Routh-Hurwitz criterion. And after applying that, you'll be able to have some conditions on Kp and Kd. So you'll be able to design a closed loop system with which can be stabilized with a proportional derivative controller. You can check it for the other options also, and you will not get the correct answer. But here in this case, I will show you what would happen. So for stability criteria, you would write this. So it would take you to s square plus 4 plus kp plus kds is equal to 0. So let's arrange it. Kds plus kp plus 4 is equal to 0. Okay. Once you have this, so for all roots to lie in the left half of the S-plane, so this is just a quadratic equation. And we already saw that uh, it just need to satisfy the characteristic of a Hurwitz polynomial. And for that, we just need to make sure, so it is of second order, and we just need to make sure that all the coefficients have the are non-zero and have the same sign. So you see the coefficient of s square has a coefficient of 1 and it is already positive. So kd should be greater than 0 definitely, and kp should also be greater than 0. So sorry, not kp, kp plus 4 should be greater than 0. That means kd should be greater than 0 and kp should be greater than minus 4. And in this way, the system can be stabilized. It would be difficult with the other cases. Okay, let's say you just took this. Let's say you just took the proportional controller. What would happen? This term would not. So I'll not do anything here. Let's say you just took the proportional controller. So what you will have is the characteristic equation would be s square plus 4 plus kp is equal to 0. You can see that there is no coefficient for s to the power 1 has no coefficient. If there is no coefficient for this, it is not non-zero, it is not non-zero, it is actually 0. Coefficient is 0. So the coefficient for s to the power 1 is 0. That means that the system is not stable. So you won't be be able to stabilize with the help of proportional controller. Similarly, when you take proportional integral controller, as in this case, you will also not have a s term here. Rather, it would take you from s square to s cube, and you would have no term for this s square. So that would create a problem. So this would give you problem, this would also give you problem, and proportional we saw that it is problematic, and this gives you all the powers of s. Hence this helps you in stabilizing the system. All right. Okay. Okay. It is desired that a closed loop system should have a settling time below 1 second. Settling time below 1 second. It requires the real part of the closed loop system to be less than. Okay. So what was settling time? We had studied it last time, and it was 4 upon zeta omega n for 2% band, 3 upon zeta omega n for 5% band. Okay. Now, what we closed loop system should have settling time below 5 seconds. What does that mean? That means let's take this condition only, 2% criteria, and in general you'll be answering this question only always for 2% criteria. Okay, so what we want is closed loop system should have settling time below this. So that means you want to have 4 upon zeta omega n to be less than 1. That means you want to have zeta omega n to be greater than 4, right? You want this condition only. Now, when we had studied this, we had a characteristic equation and we wanted to find out the poles for a second order system. It was minus zeta omega n, or yeah, so the transfer function I would say essentially before that. So closed loop transfer function that we have seen was omega n square upon s square plus 2 zeta omega ns plus omega n square. When we tried to find out the roots corresponding to the characteristic equation for this transfer function, what we got was uh, it was of this sort. So you can see that this zeta omega n has direct relation with the real part here. Okay, so here you say the zeta omega n should be greater than 4. That means the real part, what should happen with the real part? Minus zeta omega n. So zeta omega n should be greater than 4. That means minus zeta omega n should be less than minus 4. Right? So the real part of the closed loop pole should be less than what? It should be less than -4. So this is your answer. All right. I hope it is clear. Okay. I assume it is clear. So we'll move to the next question. This is a question related to the peak overshoot that we had also seen in the last class. So I hope you remember the formula. So maximum peak overshoot can be written as e to the power minus zeta pi upon under root 1 minus zeta square. And but what we want, it should be less than 15%. When you solve this, so it would be like taking log on both the sides, eliminating taking log on both the sides, then then you'll get a quadratic equation in zeta. Then you're going to find out what is the value of zeta, and you can, I don't know, you can calculate this on your own and tell me the answer, because this is just calculation based question. Take simple mathematics only. So just solve this. This is less than 0.15. What would zeta be? Please try to find an answer to this question. Has anyone got the answer? Is anyone solving even? Okay. So yeah, you have to take log on both the sides and then you have to solve the quadratic equation. So I'll tell you the answer. You'll get zeta to be approximately 0.52, and hence the option D is the answer. Okay. Okay, we'll proceed with the next question. So it says in problem 6, the constraints on the controller parameters of PD controller that would always stabilize, right? So in question 6, we had already solved this, and we can pick the answer directly from there. So yeah, we had found this answer. KD should be greater than 0 and KP should be greater than -4. So A is the answer to this question. Okay. Now we'll proceed with the next question. So in question 10, what we are doing is we have a differential equation, second order differential equation, and it is desired to design a unity negative feedback closed loop control system using a proportional controller. So it is already told to you that you're going to use the proportional controller. So the closed loop system would be stable for what? That means for what values of Kp you are going to achieve the stability for the system. So you do not need to decide any controller here. It is already given to you. Kp is already so it is already said that it is proportional control. So what? From here we can just make out that Cs is Kp. Okay. Now what we are going to do? We are going to solve this differential equation. So it would be s square ys plus 3sys minus 2ys is equal to us. Then ys upon us would be 1 upon s square plus 3s minus 2. Right? When you try to find out what is gs going to be, so it would just be multiplication of ps into cs. So this is your ps. So it would be kp upon s square plus 3s minus 2. What would be the closed loop transfer function? Why we are trying to find a closed loop transfer function? Because we want to check the stability for the same. So anyway, from a plant transfer function, deciding a controller transfer function, you have to reach to what is the closed loop transfer function. Okay. So closed loop transfer function, not transfer function, it would be like gs upon 1 plus gshs only. We are more concerned with what is the characteristic equation. So your characteristic equation is 1 plus gshs is equal to 0, right? So you can write 1 plus, what is your GS? Kp upon s square plus 3s minus 2. HS is 1. Why HS is 1? Because in the question it is already given that it is a unity negative feedback. So it is 1 is equal to 0. So what is the characteristic equation? K s square plus 3s minus 2 plus kp is equal to 0. Okay. So this is again just a second order polynomial, and checking that if the polynomial is Hurwitz or not would help us determine the stability of the system. We really do not need to go for Routh-Hurwitz because it is a second order system, and we know very well that for second order system, checking if the polynomial is Hurwitz or not would give us the necessary and sufficient condition. So, so you see the coefficient of s square is 1, which is positive. 1 which is positive, 3 which is positive. That means that minus 2 plus kp should also be positive. That means kp should be greater than 2. So you have designed a proportional controller that would stabilize the system. All right. I hope this is clear. Okay. We'll move to the next question. Okay, so it is it's saying that in problem number 10, in the last problem that we did, the ratio of ES to RS is what? So what we found out there, we found out. So how do we write this? So you know very well, YS upon RS is GS upon 1 plus GS into HS, right? Now if we write YS to be equal to ES upon ES into GS. I hope everyone agrees with this. The error into the whole PS into CS. ES. So what is YS? YS is ES into PS. Sorry, ES into CS into PS. Right? You have the error. You multiply it with controller. You multiply it with the plant transfer function. Now, this whole thing can be written as GS. That is why I've written Y is to be ES into GS upon RS is GS upon 1 plus GS HS. Cancel out GS terms. What you'll get? ES upon RS is equal to 1 upon 1 plus GS HS. So the question is asking everything about this thing only. that what would this be? So what you're supposed to find out? So let's calculate what is GS into HS. And we had already seen GS to be equal to CS into PS into HS, where HS is 1. So we don't need to bother. CS was KP and PS was, what was PS? 1 upon 3S S square plus 3S minus 2, I believe. Yes. So it is 1 upon S square plus 3S minus 2. So GS Kp in Kp upon S square plus 3S minus 2. When you try to find out what is ES upon RS, you would get it 1 plus this whole Kp upon S square plus 3S minus 2. So you'll get it to be equal to S square plus 3S minus 2 upon S square plus 3S minus 2 plus Kp. Alright. So which option matches? Uh, I think the second option, yeah, is correct. Second option is your answer when you wanted to find out ES upon RS. Okay, so this was also a very simple question. We just had to find out ES upon RS. It was just finding out error upon the reference input transfer function. Okay. So in the same problem, the steady state tracking error when the stable closed loop system is given a unit step reference input. So how do we find this out? I hope you would remember. So we know very well from here that RS is 1 by S because it is a unit step input. That is why, right? This is a unit step input. So ES upon RS was what? In the last question, I would copy this. So this was ES upon RS. When you had this, we already have yes. Now we want to put this here. So what we'll do, ES is equal to 1 upon S into S square plus 3S minus 2 upon S square plus 3S minus 2 plus Kp. Now how do we find out the steady state tracking error? So we know final value theorem, and when we apply it, what it says, limit t tends to infinity, error in time domain is equal to limit s tends to 0, s into es, right? So you can apply this here, s tends to 0, 1 upon s into s into s square plus 3s minus 2, s square plus 3s minus 2 plus kp. This s cancels out and what you get is minus 2 upon minus 2 plus kp. So 2 upon 2 minus kp. So this is your answer for question number 12, right? I hope this is clear. We had already done similar kind of question probably in last class, where we had found the steady state error using two ways. One was that we had a differential equation. We took the Laplace transform, we solved the equation, we found out the inverse Laplace, and then we had put what would happen if time tends to infinity. So there were some terms like e to the power minus 2t, e to the power minus 3t, and we went on putting them infinity, and we had got some steady state error or steady state value essentially. So that was the happening in time domain for output. Here in this case, we want to find out what is a steady state tracking error, not steady state output, steady state tracking error. And one of the ways is that we can just do it in Laplace domain because it is much easier due to algebraic nature of simplification. So yeah, S into ES s tends to 0 would solve all your problems. Okay. So again it says it is again related to the same question that what was your closed loop transfer function? In the earlier case, I'll copy that for reference. Okay. So in problem 10, it is now desired that real part of all closed loop poles be less than 1. Real part has to be less than 1. So what is the range of Kp? That is essentially being asked. So real part has to be less than 1 means definitely we have to find out what are the roots of this characteristic equation, right? Once we know what are the roots of the characteristic equation, we'll be able to say if they're how they can be made to be less than 1. Okay. So what we'll do, we'll try to find out what are the poles of the system. The pole is minus 3 plus minus b square means 9 minus 4. Sorry, this would be minus. Yeah, b square minus 4 into a into minus 2 plus kp. Okay. When you solve this, you'll get minus 3 plus minus under root of this would be 17 minus 4 kp, right? So what we can do is that we want to essentially satisfy that real part of all closed loop poles be less than minus 1. Okay, so when we try to do this, one way is that we can take this pole and keep on solving for all the poles to be less than 0. Another way is that we can choose some values of kp. For example, we already have minus 3. So anything that would disturb us is near that only. Kp is equal to 3 or kp is equal to 4 because we want to stay uh, for poles less than minus 1. So what we'll do here is, let's say we take kp is equal to 3. Because in the options we only have 1, 2, 3, 4. So we'll check for kp is equal to 3. So when you try to substitute here kp is equal to 3, you'll get minus 3 plus minus under root 17 minus 12 upon 2. So root 5 by 2. So that way you can solve and you would get the poles not less than minus 1. So what would happen is it would be minus 0.32 and minus 2.68. So one of them is not less than minus 1. So let's check for kp is equal to 4. Because when you'll check for kp is equal to 4, it would help you to shrink it down. So when you try to do this, you'll get s is equal to minus 1 and s is equal to minus 2. Okay, so what we need is kp should be always greater than 4 to satisfy this thing. So you can check this from the option. It is easier way as compared to when you try to solve this as a derivation and then find out that where are the or what is the condition on kp. So this is a relatively easier method.
Madam,
Yes.
madam, 17 minus 4k, root of 17 minus 4kp should be greater than 3.
Yes, you can do it that way.
Once tell madam.
Sorry.
Root of 17 minus 4kp should be greater than 3.
Or when did I say that? No, you do not need to see. There are two ways of checking. One is using the approach that I have shown you. One another approach is that you put conditions here so that or you get this pole to be less than -1. Okay, so like you can write it to be less than -1 and then you can go on solving for Kp.
Yes, ma'am.
Both of these ways are possible. Since we had the options, this was an easier approach. Okay. Okay. So yeah, the open loop transfer function corresponding to problem 10 is of what type? So what was the open loop transfer function? Open loop transfer function was Ps into Cs is equal to Gs. What was it? Kp upon s square plus 3s minus 2. All right. And we need to find out this is of what type. Okay, so how do we define the type of the system? So this was what that was taught to you. And this is how we approach the problem. So it is like, let's say, for example, you have you try to make the numerator and denominator in such a way that you have the last coefficient, last term to be 1. When you try to do that, basically you want to get eliminated of any s term in the last, and then you want to see what is the power of s you're getting. Like here, s cube plus 3s square plus 4s. You can take s common out of here. You see this? So s into s square plus 3s plus 4. Now you try to make the last coefficient of s to the power 0 to be 1, and you get this. So when you try to achieve the equation in this format, s to the power n times something, then what you see is that you get the type of the system. So if n is equal to 0, it is type 0 system. If it is 1, it is type 1 system. If n is equal to 2, it is type 2 system. So in our case, since we do not have anything in the numerator, and it would just lead to this equation, Kp upon, we cannot definitely take any s out of it anymore. We would just take out 2, and it would be s square upon 2 plus 3 by 2s minus 1. Let's say we take minus also out, that is also possible. But what would happen is, there is no s to the power is 0 here, right? Because you do not have anything to compensate for. Since it s to the power is 0, that means what? Sorry. Yeah, s to the power is 0 and this is n. So your n is 0. Hence it is type 0 system. Sorry. Okay. So we'll have more questions next time on type of system. From type of system, you are going to have uh, different coefficients related to different steady state error. So when you see the lectures, you will find out. So that would be very important for us. You'll get the errors corresponding to position, velocity, acceleration. That is how we define according to the uh, type of system. So we'll see that next time. So the characteristic polynomial of a closed loop system is s cube plus this, where k is the real parameter. Then the closed loop system is stable for what? Characteristic polynomial is already given to you. What is the characteristic equation here? S cube plus ks square plus 2s plus 1 is equal to 0. Okay. So what we are doing is s square s to the power s cube s square s to the power 1 s to the power 0. Okay. 1 k 2 1. Now when you try to find out what would happen, 2k minus 1 upon k, right? And when you try to find out the next time, it would just be 1. Okay. So for system to be stable, what we want? There should not be any sign change. So 1 was always positive. That so from here to here there should be no sign change. From here to here there should be no sign change. Here to here no sign change. For all no sign changes, you essentially want k from here. What you can see, k should be greater than 0. From here, what you can see, 2k minus 1 upon k should be greater than 0. That means 2k minus 1 should 2k minus 1 should be greater than 0. That means k should be greater than 1 by 2. K should be greater than 0.5. Right? So this is the way you would solve this question. And yes, we are done with the questions today. So it was already Routh-Hurwitz stability criterion. You might have all the many such questions in your assignment as well. So yeah, this would help you, and we'll have the questions related to type of systems, and probably we'll also start with root locus in the next interaction session. So yeah, thank you.
Hello, madam. Madam,
Yes,
madam, do we have allowance of scientific calculator in exam, madam?
scientific calculator. I think it should be allowed, but I'm not sure about it. You might have some mail ID where you can mail and ask for NPTEL questions, right?
Yes, madam.
So can you write a mail there asking that if all of them are allowed? I believe the calculator might be allowed, but still for confirmation, please write a mail to the NPTEL team and they'll tell you what are the rules of the exam and any doubt that you have concerning the logistics related to the exam.
Madam, for how do you get the model paper, madam? How many questions and what is the negative marking and all?
I don't think there is negative marking, but I'm not sure about it because
Yes,
since
madam.
we are TAs and we are supposed to teach you whatever goes on in the lecture, so we really don't coordinate for examinations and everything. So I'm not aware of it. So I'll suggest you that any question you have related to the exam, you should mail to the NPTEL team and they'll clarify
Once
all your
tell
doubts.
mail, madam. Once tell mail, madam.
You should have something on their site. Okay, I'll give you. I'll stop the recording.